Let me refresh your memory what we are doing. We are trying to devise equations that help us evaluate performance of different modulation schemes in additive white Gaussian noise. Right? And this is the approach we're taking. You have here the receiver. And we define signal-to-noise ratio 2 points. This signal-to-noise ratio here we call signal-to-noise ratio in the input. And this signal-to-noise ratio here we call the signal-to-noise ratio in the output. This one is defined at a carrier frequency, around the frequency of the carrier. This one is defined at the baseband. So we're looking what happens as the signal propagates through the receiver processing. And we know that what comes at the output is going to be hopefully your message signal. That's what the modulation is designed to do. But also because there is now noise coming into the receiver, there will be some noise at the baseband. And we are trying to kind of develop this relationship that tells us how the signal-to-noise ratio in the output is related to signal-to-noise ratio at the input. That's what we are after. We went through several amplitude modulation schemes. We went through double sideband suppressed carrier, double sideband large carrier with both coherent and envelope detection modulation. The last one that we're going to cover today is going to be performance characteristic for single sideband modulation. That's the one that is left. And then after that, I'll summarize all the equations that we obtained, and then we'll do a couple of examples. So let's look at what happens in the single sideband AM. So effects of noise. In single sideband AM. So let's draw a block diagram of the receiver. Remember that every one of our receivers always starts with this band pass filter, which we call front-end filter. The purpose of this filter is to eliminate the noise that is outside of the bandwidth of your signal. That's the easiest, because remember, noise has an infinite power in our model because the power spectral density is constant across all frequencies. So without this, your signal-to-noise ratio goes to 0. Right? This limits the amount of noise that enters the receiver and only lets the noise that is co-spectrum with your signal. There you're kind of out of luck, right? Because if you try to filter that noise, you're going to be filtering your signal as well. So you cannot do that, right? So you have to let the bandwidth that's allocated to your signal go through, and along with your signal, there will be some noise that comes in. Now, in a single sideband AM, what is the bandwidth of this filter? W, right? Because only W, because now single sideband has a half of the bandwidth that you need for a double sideband. And here is where I have my UX of T, my modulated signal, the noise coming in through as well. Then I perform demodulation by multiplying this by cosine 2 pi FCT, where FC is the carrier frequency. This is how I bring all of these signals to the baseband, and then I'm going to filter everything with a low-pass filter. What's the bandwidth of this filter? W as well. It's 0 to W. This is the filter that lets my signal go through. And then hopefully here I get my signal Y of T that I know from our previous studies is going to consist of some signal components and some noise components, right? So we care to understand what is the signal-to-noise ratio here and what is the signal-to-noise ratio here. So let's just write out the signals. UX of T, this is my single sideband modulated signal, is going to be AC M of T cosine 2 pi FCT minus AC M hat of T sine 2 pi FCT. This is my single sideband modulated signal. M of T is the message signal, and hat of T is the Hilbert transform of the message signal. Remember, this is how I form the single sideband AM by modulating carriers in quadrature with the message signal and the Hilbert transform of the message signal. Narrowband noise, N of T, is going to be modeled at NC of T times cosine 2 pi FCT minus ns of t times sine 2 pi FCT, where these ns and nc of t are baseband processes, each one having a bandwidth of w. And each one having the same power as n of t. Now, let's call this signal here z of t. That's the signal that is the result of the mixing of these two signals with a locally generated carrier. So z of t is going to be ux of t plus n of t times cosine 2 pi ct. Now it's going to get a little bit tedious because what I'm going to do is I will substitute, these two in here and do some math. That's a trivial math that we've done so many times. It's just that we have quite a few terms. So let's just go through them carefully, making sure that we don't make a mistake. So here I have AC m of t times cosine 2 pi fct minus AC and tenth of t times sine 2 pi fct. Then plus nc of t times cosine 2 pi fct minus ns of t times sine of 2 pi fct. And then everything here is multiplying cosine 2 pi fct. So that I can rewrite as AC times m of t plus nc of t times cosine squared 2 pi fct, and then minus AC and het of t plus ns of t times sine 2 pi fct times cosine of 2 pi fct. What did I do here? I just grouped, I look at here and I grouped these two because they're along the cosine, and then I grouped these two because they're along the sine, and then cosine times cosine, cosine squared, here's the cosine times sine. So just a simple math there. Now, let's look at the first term here. Let me say on some of my writing. You remember this cosine squared can be represented as 1/2 plus 1/2 cosine double n. Given that you have this low pass filter, what will show up in the output of the low pass filter? Just the term that is multiplied by 1/2. The rest of it is going to be located around the frequency of double the carrier, so it's going to be filtered out by this low pass filter. So I can write here y of t is going to be 1/2 AC times m of t and plus 1/2 nc of t. Let's see, are there any other components? No, because this sine times cosine gives me sine of the double frequency, and this is now double sideband modulated carrier, modulated signal that's located at twice the carrier frequency, and that's going to be eliminated by this low pass filter over there. So that's it. Believe it or not, after all of this mess, we just have two nice terms that are coming with the output. Do you have a question? Okay. So now that we have the output, let's calculate this functional relationship between the signal to noise ratios. How do I calculate signal to noise ratios? Signal to noise ratio at this input point is going to be power of ux of t divided by the power of n of t. Okay? What is the power of ux of t? It is the power of this guy. Can you look at it and tell me what it is?
Square.
You're going to square, so it's going to be 1/2 AC squared times m squared of t averaged over time plus 1/2 AC squared m hat of T averaged over time, right? That's what you have the first and second. When you square it, there is a 2 times m of t m hat of t cosine times sine. But this is a, again, double sideband suppressed carrier signal that has no DC component. Therefore, the signal, average of that signal over time is 0. Right? So this is what the power of Ux of t. How about the power of the noise? If the power spectral density of the noise is n0, what is the bandwidth? Bandwidth is just a W. So this is the power of the noise. And that's what happens at the input. I can simplify this somewhat by realizing that Hilbert transform does not change the power of the signal. Remember, it does not change the magnitude of the sinusoidals that build that signal. It only changes their phase. Therefore, the power stays the same because power does not depend on phase. Right? So this m hat squared of t is the same as m squared of t. So you have 2 terms, but they're equal, right? So I can rewrite this as AC squared times the power of the message signal divided by n0 times W. Very neat expression here. Okay, so let's now look at the signal to noise ratio, the output. This one is going to be power of the signal part of this. So you can see here I have 2 parts. This is signal and this is noise. So power of 1/2 AC m of t divided by power of 1/2 NC of t. Now the power of the thing upstairs is going to be 1/4 AC squared times m squared of t averaged over time. Power of what I have downstairs is going to be 1/4 times NC squared over t averaged over time. I can simplify this even further. I can cut these 1/4 because they're the same upstairs and downstairs. So I have AC squared. This is power of my message signal. Now I have downstairs the power of NC squared. But what do I know about the power of NC, about signal NC? What do I know about that power? One of the important results. I know that the power, let me put it here, recall, NC squared of t is the same as ms squared of t is the same as n squared of t. And this one I know how much is. How much is the power of the noise? W times n0, right? So here it's W n0 times W. All right. So I have the signal to noise ratio, the input, the signal to noise ratio, the output. What can you tell me about these two?
The same.
They're the same. So in the case of a single sideband, AM, I have that the signal to noise ratio and the output is the same as the signal to noise ratio. That's a very nice result, right? Now, I want to point out something here. We discussed, and this is just a hint, we're going to go and give this much more thorough look, but you should already kind of have this observation at this point. We have 2 types of approach to modulation in AM. You have double sideband and you have a single sideband. Let's say we restrict ourselves to double sideband suppressed carrier and single sideband AM. Double sideband suppressed carrier uses twice the bandwidth, right? But what did I observe as far as the signal to noise ratio? There's a 2 times improvement, you know, in the receiver processing, right? This one uses W, half a bandwidth, but also gets half of the improvement, right? So there is something there, and what you're going to find out is there is a very important relationship in communication, and we're going to spend a lot of time, especially in digital communication, talking about it. But even now, I want to point it out. You can actually do a trading between power and a band. Let's say you want to go large distances, right?
you can actually use narrowband signal, but then you need a lot of power to reach the largest. Or you can use a wideband signal, but then your power goes down, the power spectral density goes down. So we're going to go look at that in much more detail, especially when it comes to FM and later on in your studies when it comes to digital communication. But at this point, we have finished all the analog modulation schemes. Let me provide you a summary in one spot so that you have all of these input-output relationships, and then we'll do a couple of examples of application of this. So, summary. We have 1, 2, 3, 4 modulation schemes that we covered. The first one was double sideband suppressed carrier. What was the signal to noise ratio in this one? Signal to noise ratio at the output. Let me move this closer. Why am I wasting the space on the board? So this is a signal to noise ratio at the output. In this case, was 2 times the signal to noise ratio at the input, and your bandwidth was 2 times double. Right? Also, we can say the power of the noise is N0 times 2 double, where N0 is the power spectral density of the noise. So this is the result for double sideband suppressed carrier. Double sideband large carrier, we had 2 options. We have coherent and envelope detector. Right? Coherent means that you are demodulating by using a locally generated carrier that has the same frequency and the phase as the incoming. Right? That's the easiest way mathematically, but it's relatively hard practically because you need to extract the frequency and the phase. But in this case, we obtained that your signal to noise ratio at the output was 2 times a squared power of the massive signal normalized, 1 plus a squared power of the massive signal, and then times signal to noise ratio at the input. Okay? And here the bandwidth was the same as upstairs, 2W, and noise in the output was N0 times 2W, where N0 is the power spectral density of the noise at the input. We did analysis of what happens when you have an envelope detector, and what we found out surprisingly that you get the same relationship here. It's 2a squared power of the massive signal normalized, 1 plus a squared power of the massive signal normalized, signal to noise ratio and input, with the same bandwidth of 2W, and power of the noise at the input is 0.2W. But this relationship held the condition that signal to noise ratio at the input was large. Remember, one of the assumptions that we have is that the noise is small to begin with, then you get this kind of relationship between these two. This is usually the case because we, usually operate the signal to noise ratios that are 20, 30 dBs at the input, in which case, you're going to be okay. And then the fourth one we covered today. This was a single sideband AM. Single sideband AM. In this case, you have the simplest relationship, the signal to noise at the output. was the same as the signal to noise at the input. Bandwidth, in this case, was just the W, and the noise power was N0 times W. That's a summary, right? These are the four relationships that we added to our knowledge about these systems. Now we have complete understanding of each one of them, at least at the theoretical level. We know how you modulate, we know how you demodulate, we know the spectral footprint, and we know the performance index. So these are all the things that we need to know about the modulations. Any questions here?
Could you remind me what A squared is again?
A is a modulation index.
Oh, that's right.
If you remember, let me just refresh your memory here. Note. We have U double sideband large carrier of T as AC, 1 plus A normalized message signal times cosine 2 pi SCT. So that's the format of our modulated signal. A is what we call index, it's between 0 and 1, and Mn is the message signal that is normalized to the maximum of its amplitude, so that Mn essentially takes values only between 0 and 1. Oh, sorry, minus 1 and 1, which forces this whole term to always be positive, right? And that enables us to use envelope detect. Okay. Let me work an example. This is example 511 from your textbook. Let us get some feel. How you use some of these equations. So we're looking at M of T that has a bandwidth of 10 kilohertz, that has a power of 16 watts, but the maximum of magnitude of M of T is equal to 6. Then we're sending this signal through a channel. Channel adds attenuation of 80 dB, and channel is corrupted by with a noise that has a large spectral density, 2 times 10 to the minus 12 watt per hertz. Required signal to noise ratio at the output needs to be 50 dB. So very tough requirement. That's you know, 50 dB. That's 10 to the 5, right? So this is 100,000. The signal needs to be 100,000. The power of the signal needs to be 100,000 times above the power of the noise. It says here, calculate the transmit power required TX power for double sideband, large carrier, double sideband, suppressed carrier, and single sideband AM. For double sideband large carrier, A is equal to 0.8. Double sideband large carrier. So this is what we are asked here, is to kind of compare these and understand what their transmit power requirements are in this case. Now let me sketch what the nature of this problem is. And I'm, since I'm kind of wireless guy, I'm going to sketch this in terms of wireless. But it's the same in wireline, just the channel is different. Right? You have your transmitter, right? Transmitter, let's say in this case, goes through a broadcast antenna. And there is a certain power, let me call it transmit power, at which you're going to transmit your signal. If you look at propagation of this signal, this is some distance between transmitter and receiver, you're going to transmit at a given power level. Let's say this is your transmit power level that you're going to have at the transmit antenna. as you propagate along this distance, your power is going to be decreasing, right? As you go further and further, your attenuation, accumulates, and your power of your signal goes smaller and smaller. Let's say you have your receiver at this point, and this is my output. There is a noise in the channel, right? The noise is at the same power level, right? Regardless of your signal. It exists everywhere. It's a function of essentially the C. So you have the signal to noise ratio defined at this point. Who dictates this signal to noise ratio? Your customer, your end sync, right? If I'm listening to it, it better have a, let's say it's a voice, it better have a signal to noise ratio of output that's 40 dB. If it's a let's say analog television, it better have a signal to noise ratio which is 50 dB, otherwise I still start seeing snow and I start seeing degradation of images. And then the various communication systems would have a different signal to noise ratio requirement at the output. That's just dictated by whoever is the end sync of the information. Usually it's us. Now, based on a modulation scheme that we use, this signal to noise ratio at output is going to translate into requirement for the signal to noise ratio in. The same signal to noise ratio at the output, depending on the type of the modulation scheme that you use, is going to translate into different signal to noise ratios at in, right? Because every different modulation scheme has a different processing gain, right? So because this processing gain change, or that function, over there changes, then the signal to noise ratio is going to be different. Now, let's say this is a point of the receiver. This is the signal to noise ratio that I'm talking about, right? This is the power of the noise. This is the power of the signal, and that's the signal to noise ratio that you need to have. So now, if I'm taking this receiver and I'm kind of traveling away, here I'm having excellent signal to noise ratio, my reception is perfect, right? And then you travel, and eventually, this signal to noise ratio degrades to the point where you have no reception anymore. And that's the boundary of your coverage, right? That's why these calculations are extremely important, because they help us find the limit of the communication. How far can I separate the transmitter and receiver before I lose my signal, right? Now, this attenuation here is the property of the channel. In my case, this is given as 82. And usually, although I formulated the problem, in a logical sense, from left to right, I'm transmitting and I'm kind of wondering how far I can go before I receive. Usually the problem is always posed to us different. They want to say, okay, I want you to put the radio station on this tower, and I want you to cover all the way to Orlando, right? So then you actually start by drawing a circle and say, okay, I need to be able to get there. I know what my channel is going to introduce in terms of attenuation. I know what the performance of my receiver is. Can I calculate how much I need to transmit, right? And then you add some phase margin, and this is how much you need to transmit, right? So you kind of we work these problems as engineers. We work them backwards, right? We start from the receiver and go all the way to the transmitter and calculate how much do I need to transmit to meet certain coverage requirements or performance requirements, right? And this kind of calculations are known as lean budget calculations. You probably heard of people talking about them, but it's there. Once you get it, it's really, the complexity of this is kind of on the order of balancing the checkbook, right? You have that's why they're called budget kind of problems. It's at the same time one of the simplest and one of the hardest problems, right? Especially when it comes to check. All right, so let's go and look at our modulation schemes and work this problem for all the types that we covered, and this will give us some idea about how do they compare amongst each other. So let's first look at what happens in the case of double sideband suppressed carrier. And I have in my notes mistake right away. So in this case, signal to noise at the output is equal 2 times signal to noise at the input, right? So from here, I can calculate signal to noise at the input. It needs to be 1/2 of the signal to noise at the output, right? This is from my receiver here. That's this relationship here. Now, if I express my signal to noise ratio at the input in dB, what is the value? If the output signal to noise ratio is 50 dB, what should be the signal to noise ratio at the input? 25?
No. 10
10 log.
So half, how much is half? Minus 3 dB, right? Let's remember this. 2 times is 3 dB, right? 1/2 minus 3 dB. Okay? Let's say 10 times is what? 10 dB. 0.1 is equal to what? Minus 10 dB. 100 times how many dB? 20 dB. 0.1? 0.01, sorry. Minus 20. Okay, 10 to the n. N times 10 dB. 10 to the minus n is minus n times 10. Okay, at least these you need to know. So, if the signal to noise ratio is 50 dB, and your signal to at the output and your signal at the input, signal to noise ratio at the input needs to be 2 times better, that means it needs to be better by 3 dB. Actually, it can be 2 times worse, right? So it needs to be smaller by 3 dB. So it can be 47 dB, right? So what that means, if I supply signal to noise ratio here of 47 dB, my receiver processing will improve that signal to noise ratio by 3 dB. So what I present to the end user is going to be 50 dB, which was the target. Now, what is my signal power at this point? Well, we start from the bottom and say, well, what is the noise power? N is going to be 10 log of N0 times the band, right? If I want to express this in logarithmic units, which is usually how we do these kind of problems. So now this is 10 log. N0 is 2 times 10 to the minus 12. 2 times 10 to the minus 12 watts per hertz times the bandwidth. The bandwidth we said was 2W, so it's going to be 20 kilohertz. So it's going to be 2 times 10 times 10 to the 3, so 10 to the 4. And how much is this? Well, you have 10 to the 4 and 10 to the minus 12. That's 10 to the minus 8, right? So it's minus 80 plus 3 minus 77 plus 3 minus 74, right? So this is minus 74. Units are dB with respect to watt. Okay? Now, did you follow this? Let me go through it again. You have 3 terms here. You have 10 to the 8 as the first term, 10 to the minus 8. 10 log of 10 to the minus 8 is minus 8. And then you have 2, so that's 2 times better than that. So it's 3 dB better than minus 80, which is minus 77. And you have again 3 dB better minus negative 77, which is negative 74. The units are watts, so it's dB relative to the watt. So that's my noise power. Now, what should be my signal power? signal power is going to be whatever is the noise power plus whatever I require for signal to noise ratio. My noise power is minus 74 dB watt, plus my requirement for signal to noise ratio input is 47 dB. And that gives me that my signal at the input of this receiver needs to be at minus 27 dB watt. Now let me ask you a tricky question for people that work in propagation and PCS. How many dBm is this? Three? No.
Minus
No?
27 plus 30.
Actually, sorry. Three.
3.
Three dB. All right. So that's dBm. So that's the requirement in terms of the signal power. So now, if I look at this is a signal at the receive point. This is this. All right. So that's this guy. SRX. So how big is STX? How much do I need to transfer? So STX expressed in dB is going to be whatever is SRX expressed in dB plus the path loss, dB watt here. Is going to be whatever is SRX expressed in dB watt plus the path loss expressed in dB. In our case, this becomes minus 27 dB watt plus path loss of 80 dB, and this gives us what? This gives us positive, right? This gives us 53 dB watt. 53 dB watt. So STX 53 dB watt. That's 10 to the 5, 2 times 10 to the 5, right? So it's 200,000 watts or 200 kilowatts. Right? So 200 kilowatts. That's the transfer power that we need to transfer, right? This is a very large number, right? Very large number. But it's what we do. You know, in the broadcast world, we measure power usually in kilowatts. For example, some high-powered analog TV stations, they can be 1,000 kilowatts, 1 megawatt, right? Analog broadcast stations are on the order of, I'd say, from 10 to several hundred kilowatts of the power that you transfer. Now, I don't know if you're aware, but right now we're going through a major conversion. We're taking off the air all of our analog TV stations and we're putting in a digital TV station because of the digital modulation and much smaller requirements. Your signal to noise ratios are now going from 40, 50 dB into around what they're like 15 dB. So your digital television needs 15 dB to operate properly. So that means that these powers are becoming much, much smaller. And typical digital TV broadcast station is limited to 15 kilowatts. But it's still kilowatts, thousands of watts. Right? So that's what we are transferring. Let's look at the next example, single sideband AM. I'm just going to do the same sort of calculations as I did here. In this case, signal to noise ratio, the input needs to be what? Needs to be the same as signal to noise ratio. The output needs to be 50 dB. Why? Because there is no processing gain in the single sideband. Whatever you feed in, that's what you get out in terms of the signal to noise ratio. the noise power in this case is going to be 10 log of the noise power spectral density times the bandwidth. Bandwidth in this case is just W. So this becomes 10 log of 2 times 10 to the minus 12 baud per hertz times this W here is 10 to the 4 hertz, and this gives you minus 77 dB baud, right? That's the noise. And then here, your signal at the reception is whatever is the noise power plus the signal to noise ratio requirement at the input, which is minus 77 dB baud plus 50 dB, which gives you minus 27 dB baud. And then your S transmit needs to be your S received plus the path loss, everything expressed in dBs. So it becomes minus 27 dB baud plus 80 dB, which is 53 dB baud. Okay? And then here, that's essentially, if you bring this in linear domain, this is 200 kilohertz, right? So here, the story is the same, right? You have, this is that trade-off that I spoke about a little bit earlier. You have a smaller bandwidth, right? But because of that, you need a higher power density, right? You're transmitting the same power, right? So the density of the power is twice here, right? Because you're spreading these 200 kilowatts over half a bandwidth relative to this one. The last one I'm going to consider here is double sideband large carrier. Let's look at that guy. So double sideband large carrier. Here we have that the signal to noise ratio at the output is going to be equal to 2 times a squared power of the message normalized, 1 plus a squared power of the message normalized, times signal to noise ratio at the input. Right, that's our relationship in the case of double sideband large carrier. So from here, I can calculate the signal to noise ratio at the input as 1 plus a squared power of the message normalized divided by 2 a squared power of the message normalized times signal to noise ratio at the out. Right? Now, the question here is a squared, I know, because a is given to me, but what is the normalized power of the signal, right? I have this from this here. I have that m squared of t is 16 watts, right? And then I have that the maximum of the signal is 6. So what is normalized? It's going to be m of t divided by 6, right? This brings this signal back to range between -1 and 1, right? This number 6 is what will normalize this signal. So if I square both sides here and I average over time, I get m squared of t average over time is 1 over 36 m squared of t average over time, right? Or I can say that the power of the message normalized is going to be 136 of the power of the message, which in this case is 16 divided by 36 watts. Okay? So that's the power of the normalized message signal. So now I can plug this in here, and you get that the signal to noise ratio and the input needs to be 1 plus 0.8 squared times 16 over 36 divided by 2 times 0.8 squared times 16 over 36 times signal to noise ratio and out. This number, when you calculate it, is 225. Or, if I want to say signal to noise ratio at the input expressed in dB is going to be 10 log of 225 plus signal to noise ratio at the output expressing dB. This one is 50, so 10 log of 225 is 3.5. So this is 3.5 plus 50, which is 53.5 dB. One thing that you notice here is that your signal to noise ratio, the input, needs to be better than the signal to noise ratio, the output. Can you remember why was that the case? Because what? Processing gain is smaller, right, than 0 here, right? 0 dB. It says that the input signal to noise ratio needs to be larger than the output. Where are we losing? What is so?
In RX?
So why do I have to have input signal to noise ratio better than output? Where is the loss? No.
Okay, well,
Think about what makes double sideband large carrier. So what is that one? The carrier, right? So here's what is happening double sideband AM. I'm sending, you can see your signal is composed of 2 components. One is the actual information, which is M of t cosine 2 pi of ct, right? But there is embedded in there just a pure sinusoidal that sits in the middle. That's your carrier, right? Large carrier piece. In the receiver processing, large carrier is thrown away, right? It is only used to drive the envelope detector, right? It is not of no use at all. And the big portion of the power that you're sending in your transmission belongs to that carrier. And it's that power is part of the signal at the input, but it's removed from the output. Carrier is just tossed away. It's not used. You don't present carrier to the end user. So that's why this one has a negative processing gain, or processing gain smaller than 1. Now that you have, I'm just going to use this section to complete these calculations. Now that we have what the signal to noise ratio of the input needs to be, we can easily calculate the noise. Noise is going to be 10 log of the power spectral density of the noise times 2W, right? Because this is still double sideband, and it's essentially the same as this noise here. So this is minus 74 dB watt. And then the signal at the receiver is going to be noise plus signal to noise ratio at the input, which is going to be minus 74 dB watt plus 53.5 dB, which gives you minus 20.5 dB watt. And then signal for transmission is going to be whatever I receive plus the path loss in dB. So in this case, this is minus 20.5 dB watt plus 80 dB that I need to overcome due to the path loss. And this gives me a value of 59.5 dB watt. When you translate that into linear, 59.5 is almost 60 watts. It's 1 billion watts, right? 60 dB watts is 1 million, 10 to the 6. If you do calculation more precisely, this gives you a value of 900 kilowatts. So almost 1,000 kilowatts needs to be transmitted on this. And you can see that this is reflected dearly in your power bill, right? Because you have because you're sending a lot of power, which is essentially wasted, right? Your carrier, your power requirements go up, but where do you recover it? You recover that in effect that your receiver is now costing $5 or $2 because it's single diode that drives the capacitor, right? So it's not complicated receiver, and you can easily demodulate the signal. Any questions? Go ahead.
For the signal to noise, how comes we didn't use the formula provided to us in the summary for the example?
Where?
The, what do you call it, the noise equals N0 times 2W? Oh, it's the same thing, it's just.
Yeah, this is and not times 2W.
Okay, yeah, it's in dB, the other one is in linear, I'm sorry.
Yeah.
I didn't notice.
Yeah. What was the question?
You said there is a trade-off between the single sideband and the double sideband, but I see the power from the transmitter is equal to 200 kilowatt.
Let's draw this in the spectral domain. This is double sideband. You have a bandwidth of 2W. You have a power that's 200 kilowatts, right? So this area under the curve is 200 kilowatts, right? Right? Why? Because you remember the power is in an integral over F of the power spectral density. That's our general expression, right? With that with. Now this is for double sideband suppressed carrier. For single sideband, how does this look? Here's your frequency. Now this is FC and this width is 2W. Right? Now here's your carrier frequency FC, and here's your W here, half, right? So this is W. Your power, total power needs to be the same. So the only way to make that is now this is W. So this needs to be 2 times of S in this case, right? Double power spectral density. So power is the same, indeed, right? But because you are shrinking the bandwidth, your power spectral density goes up. So that's the trade-off I was referring to. So it's the power spectral density that we're talking. Okay.
But the total power to the transmit is equal.
Is equal, yeah, because they, what the better, most often what we do is we don't talk in terms of power, we talk in terms of the signal to noise ratio, right? So here, the signal to noise ratio is twice that signal to noise ratio here because your bandwidth is 1/2. Okay. All right. So we're done with analog. That's where easy stuff. These were relatively easy, but it's very nice, in terms of understanding what is actually happening here. We need to do the same task now for FM modulation. And just like we had problems in determining what is the spectral footprint of the FM modulation signal, here we're going to have the same kind of challenges because FM modulation is not a simple translation of the spectrum from baseband to the passband. It's quite non-linear in nature. So just like in the case of the bandwidth determination, we're going to take it one step at a time. First, I'm going to look at, what happens if I have my signal and a parasitic sinusoidal component in the vicinity of that signal. And we're going to be able to calculate what happens then. And then we'll look at what happens if I have multiple of these to get a feeling, and then we'll generalize this to the case of the FM signal. So we'll walk 3 steps before we get to the final result. But just like anything else, every journey starts with the first step. So let me first look at what happens in the most simple case.
So effects of noise in angle modulation. So here, I guess I'm going to limit the scope just FM modulation. I'm going to consider only FM. Phase modulation is not common. I'm not aware of any system that uses phase modulation for analog transmission. On the contrary, in the digital transmission, phase modulation is used all the time. It's the dominant type of the modulation. So just to make this a little bit more practical, I'm going to limit the scope to FM and just treat the FM modulation. And we're going to, so that's the first one, and I'm going to assume that, so this is the first, and the second, the systems we consider have high signal to noise ratio at the input. So again, the same kind of assumption that I used in a double sideband large carrier with the envelope detector, I'm going to assume that you're working with relatively high signal to noise ratio in the input. And and you can sense what is going to happen. Based on this assumption, I'm going to do some simplifications, and I'm going to neglect some terms that bother me along the way, right? But we're going to actually, once we get everything done, we're going to revisit this assumption, and then kind of put some thresholds that we can say below this threshold, this doesn't work. Above this threshold, this whole theory that we present here works. So problem is going to be approached in 3 stages. In the first stage, I'm going to look at just a parasitic carrier. Parasitic, I'm kind of trying to simplify the notation, but this is going to be a carrier with a parasitic interference, and I'll specify that in a second what that means. So it's going to be carrier plus parasitic interference. So that's going to be the first case that we're going to consider. Then we're going to consider carrier plus sum of parasitic interference. And in the last iteration, we're going to look at carrier plus noise. That's going to be our last step. And even there, just like we've been doing so far, we're going to assume that the noise we're facing is white Gaussian noise with a flat power spectrum. So let's look at the first case. So case 1, unmodulated carrier. Plus parasitic component. So my signal here, R of t, is going to consist of 2 parts. AC, this is subscript, AC cosine 2 pi FC, which you recognize as unmodulated carrier. And I'm going to add to this guy as a component that has a magnitude UN, cosine 2 pi, has a frequency F plus Fn, Fc plus Fn, and do I add the phase? No, just keep it. Right? So that's my parasitic component. So I have a carrier, and this is the parasitic
this component has this offset of Fn. This is the how far it is from the carrier, right? It is still within a bandwidth of the received signal, but it is not at the frequency of the carrier. It's slightly off to one side. Now, what is the big idea here? And you should kind of be able to understand it. We have a complex problem. I have a signal plus noise that enters the FM receiver. But here's what I'm thinking. Okay, let me put this problem aside. I put my Fourier glasses. I really looked at the noise. And I say, well, you know what? The noise is nothing but a whole bunch of very small sinusoids, right? So I say, okay, well, let me see what happens if I have just one sinusoidal, you know, corrupting my input signal, right? And I'll present that, and I'll be able to do the math all the way through. And then I say, okay, I understand now what happens to a single sinusoidal. Let me put a whole bunch of small sinusoids, right? And then if I keep on putting more and more sinusoidals, I'll eventually get to the noise, right? So that's the thinking here. So kind of approaching this kind of feeling in the dark, right? You're in a dark room, and then you can say, oh, okay, there's a you know, chair here, and there's a desk here, and then eventually you realize I'm in a classroom. Right? So that's how we're going to do it. We're going to look at what happens to one sinusoidal, what happens when I have a whole bunch of them. Then we're going to say, okay, now that I understand, let me make infinitely many of them, make them infinitely small, infinitely tight, all of that, and then in the limit we're going to get what happens to signal to noise ratio. Okay, so that's our signal. We know that this can be rewritten as something like this: AC cosine 2 pi FCT plus UN cosine 2 pi FCT times the cosine 2 pi FNT minus UN sine 2 pi FCT times sine 2 pi NT, right? What did I do? Nothing smart. I took that cosine to the right hand side, realized it's a cosine of the two angles, and then I applied cosine alpha or plus beta 3 identity. But now I can take this one step further. So I can say, okay, look at these things that are with cosine, right? So I can say this is AC plus UN cosine 2 pi FNT. And this thing multiplies cosine 2 pi FCT. And the other one I leave alone, so it's UN sine 2 pi FNT times sine 2 pi FCT. And whenever you see me do this, you know what happens next, right? When I put this in A times cosine plus B times sine, I'm going to determine the amplitude and phase, right? Merge these two into a single cosine. So I can rewrite this as, I can say something like this: AC plus UN cosine 2 pi FNT quantity squared plus UN squared sine squared 2 pi FNT 1/2 times cosine 2 pi FCT plus arctangent of UN sine 2 pi FCT divided by AC plus UN cosine 2 pi FCT. Okay. Now, at this, if somebody walked in at this point, they would say, "Oh my God, this guy is like some mad scientist, right? Knowing all of these formulas." But you see, it's just it's an easy stuff. It's just just cumbersome to write. But you see here, A cosine plus B sine. It's A squared plus B squared. Take the square root times the cosine, whatever is the angle, minus arctangent over B over A. right? That identity, we use that identity quite a few times. Now, when you're faced with this, then it's kind of already at the limit of what we can manipulate analytically. So we invoke our assumption here. We assume that the signal-to-noise ratio, the input, is high. Practically what that means, or signal-to-interference is high. Practically what it means is this, the AC here is much, much greater than UN, right? I have a strong carrier and a small sinusoidal component that is surrounding the carrier. But before we go there, what you realize is this. R of t is m of t times cosine 2 pi fct plus this psi of t, where m of t is this piece here, the magnitude, and psi of t is this piece here, the changes in phase. Now, the big understanding here is this: the presence of this parasitic component modulated my signal, right? And it modulated both the amplitude and the phase. Now, when I have signal received by the FM receiver is smart. It knows where the information is. Where is the information for FM receiver? Is it in the magnitude? No, the receiver knows. Whatever is changing the magnitude, it's not a signal. It has to be noise. So I'm going to try to ignore the changes in the magnitude. And I'm going to just try to demodulate whatever is in the phase. So, let's simplify this, and then we'll draw a structure of the receiver, and you will notice that there is an additional component that we put in there to eliminate these variations in them. But for right now, we will consider that AC is much greater than UN. If that's the case, your M of t, which is equal to, I can just get it from here, it's AC squared plus 2 UN AC cosine 2 pi Fnt plus UN squared cosine squared from here, and sine squared from here gives you 1. So this is the UN squared, take a 1/2. And then I can say this is approximately AC 1 plus UN of, well, let me take one more step. I can say this is equal to AC 1 plus 2 UN over AC cosine of 2 pi Fnt plus UN squared over AC squared taken square root. All right, what did I do? I just took AC out of the square root. Now, this is small, right? So I'm going to say this is approximately 0. And we had this before. Let me see if you remember. 1 plus x to the 1/2 is approximately what when x is small? 1 plus what? Hmm? 1 plus x for small x.
Little x.
That comes here. But what is coming? What is here? Hmm? There you go. Excellent. All right. In general, one plus x to the power of alpha is approximately 1 plus 1 over alpha, that is x, plus all x. I wonder if that's the case. Yeah, I think so. That's the McLaurin series for 1 plus x to the power of alpha around 0. Actually, see, I made a mistake. It's alpha. It felt uncomfortable, you know, because 1 plus alpha x plus all x. So that's the marker. So let's apply that to this one. I get m of t is approximately AC. Now I have 1 plus this to the power 1/2, so just 1/2 of this, right? And this is 1 plus un divided by AC cosine 2 pi Fn. So that's the shape of my magnitude. And then let's do the same thing with the phase. This psi of t was arctangent of un sine 2 pi Fn t over AC plus cosine, un cosine 2 pi Fn t, which is approximately arctangent of un over AC times sine 2 pi Fn t, which is again approximately, what's arctangent of something small? Arctangent of x when x is small. Arctangent of x is approximately what? I know it's 0, but what's to the first order approximation of 0?
Sine or sin?
Arctangent of x is approximately x. Right. Remember, this is the story, right? F of x is equal to f of 0 plus f prime of 0 over 1 factorial times x plus f double prime at 0 over 2 factorial plus x squared times x squared plus f triple prime of 0 over 3 factorial times x cubed and so on, right? That's the Maclaurin series expansion for any function, right? So what's arctangent of 0 is 0, so the first term is 0. What's the arctangent at the derivative at 0? So arctangent of x, what's the derivative of this? Is 1 over 1 plus x squared, right? That's the derivative of arctangent. So when I evaluate this at x equal to 0, what's the value? The value is 1. So from here, you get that arctangent of x is approximately, the first one is 0, plus this derivative 1 times x plus all of x. That's the first order approximation for our arctangent. So here, now using all of this, we get that our psi of t is un divided by AC times sine of 2 pi fc t. So finally, I can simplify my r of t as AC 1 plus un over AC times cosine of 2 pi Fn t times cosine of 2 pi Fct plus un over a times sine of 2 pi Fn t. So that's the approximate relationship for my CFC. Now, assuming the high input signal to interference ratio. Okay, any questions so far? Okay, so we now need to take this signal and present it to the FM receiver and see what comes at the output. I'm going to stop here, you can have a little break, and then we'll continue after the break.